Welcome back to part 2 of Custom Recursive Vellum Emission. In this part, we're going to take the simulation we created in part 1 and point Deform our original geometry back onto the simulation. If you haven't watched part 1, I highly recommend you do that first, otherwise a lot of what we'll go through today might not make any sense. I'll leave a link to that in the description. So here on the geometry level, I've taken the liberty to cache out the simulation. I'm bringing in the geometry as well as the points being scattered that copies new Vellum geometry and constraints into the simulation. I'm then removing any attributes and groups that we don't need using the clean node. And the important attributes I'm choosing to keep are the point ID attribute, the name attribute, as well as the velocity. And for the scatter points or the spawn points, I'm keeping the point ID, the name, as well as the orient and the p-scale. I'm then creating a group that we can use to split our geometry post-caching. After that, I'm just merging these geometry streams together, and then I have a file cache where I'm baking the geometry to disk. After the cache is done, I'm splitting this out so that we get our geometry on one side and our spawn points on the other side. I'm going to append a point deform node. And in order for this to work, we need 3 components. In the first input, we need the geometry to transform. I'll add a null to the instances before they get remeshed, and I'll call it outGeo. I'll then add 2 object merge nodes that we can use to reference the original geometry as well as the spawn points. And the reason why I'm doing it this way and not just wiring it in directly is because I'd like to avoid any overcrossing wires. We can then drop down a copy to point sop and wire these 2 outputs. Now, in order for the point deform to do its thing, we need the geometry that we want to deform to appear at the same time as the Vellum geometry appears in the simulation. So right now, if we hit play, we can see that we're currently copying over that same geometry on our points. After the copy to point sop, I'll drop down a solver sop. This is pretty similar to how the sop solver in DOPS work, where we can perform sop level operations, except this node lives in sops. As many of you probably already know, the sop solver is actually DOPS in practice, but it allows us to work on the sop level with ease. Just like we did in DOPS, I'd like to have an age attribute so that we can record how long each copy have been in the sim. So I'll create an attribute create node, and I'll pop it into the spawn points, and here I'm just going to call this attribute age, and the default value of 0 is fine. I'll then hop down into the sop solver, and in here we have access to the previous frame. I'll merge the result from the previous frame with the first input. And after the merge, I'll append an attribute wrangle. And this wrangle we can call calcAge. In the wrangle, I want to take the age attribute and increment this by the time increment. If we now jump up to sops again and toggle the solver, we can see the geometry being merged over and over again. Now, because the amount of objects needs to match whatever is happening in the Vellum simulation, we need to take that Vellum interval into account. Right now, we're merging geometry on every frame, and in the Vellum simulation, we're actually only emitting every other frame. So what I'm going to do is I'm going to go back to our .NET and hop in. And then if I go to the Vellum source node, I'm just going to copy the first part of this expression here. And then if I head back to the solver sop, I can create a switch node. On the left side, we're going to have our first input. And then on the right side, we're going to have a null. And then I can paste the expression into the switch node. But instead of checking if it's equal to 0, I'm going to check for whenever it's not equal to 0. So now we can see that whenever it's not supposed to emit, it will return the null. And when it is supposed to emit, it'll return the first input. Let's jump back up. And after the solver sop, I'm just going to drop down an attribute delete. And here I'm going to delete everything aside from the name, PID, p-scale, and age. We can then pipe this into the first input of the point deform node, since this is the geometry that we'll want to deform. The second component that we need for this to work is a rest state of the sim geometry. So I'm going to go to my copy to point sop first, and I'm just going to hit this piece attribute so that we get the corresponding piece. And then what I can do is I'm going to grab these 3 nodes and copy paste them. But instead of the original geometry, I'm going to grab the out instance source. And this is the remesh geometry that we're feeding into the sim. And before I plug this in, I'm just going to unpack this. We can then pipe this into the second input of the point deform. The third and final component that we need will be the cache sim. I'm also going to copy this object merge one more time, and then we'll just grab the sim geometry. And this we can plug into the third input. And in the point deform, I'll want to specify that PID attribute in order for the point deform to match each piece. If I now hit play, we can see that our original geometry is being deformed by our sim geometry. One thing I will do though is I'm just going to decrease the radius a little bit. And now we get a little bit of a better result. After the point deform, I'm going to transfer the velocity from our Vellum sim. We can do this with an attribute transfer node. And in here, I'm just going to specify v, because that's the only attribute I want to transfer. If we want to visualize the velocity, we can just hit this button here. So this will ensure that we get somewhat accurate motion blur when we render. And in my final render, I think I added a delta mush just to smooth out any weird wrinkles or inconsistencies in the mesh after the point deform. I think I had the iteration set to 8, and the step size, I lowered that to 0.1. And then I just realized that I messed up the attribute deletes here. So instead of and PID, this should be this hat, and we should have a space in between. Same goes for this one. So previously it was actually just disregarding this PID attribute and just deforming it based on proximity. Doesn't seem to make a difference visually in this case, but now at least it should respect this attribute. The next thing I'd like to address is to make sure that the geometry gets scaled from 0. As you can see now, they're sort of like each time a new object gets emitted, they sort of pop into frame. So let's fix that. For this, I'll need to extract the centroid. And by default, it'll just extract the centroid and create a point where the centroid is. But we actually don't want this. We want this to first off be running over our PID attribute. And then we're going to change the piece elements from primitive to point. And then instead of outputting points, I just want to output an attribute. So now we can check that we have a new attribute called centroid, which contains the center coordinate for each object. Now, when I have the centroid, I can create a new wrangle. I'm going to start by declaring a new variable called mask. And then we can do a similar fit function to what we did in DOPS. So we have the age attribute, and I want to remap it from @timeinc to, let's say, 0.1. So it'll be a pretty fast transition. And then I want to output this to be between 0 and 1. And if we want, for shading purposes, we can also export this mask. And then finally, I'm going to transition from this centroid attribute to our final position. So I'll say v@p equals lerp, and we're going to start on our centroid, and we'll end up on our position. And then we'll let the mask control this. So if we look now, you can see that they start from nothing and then they scale up. And then if we want, we can just visualize this transition with a color swap. Change the color type from constant to ramp from attribute, and then I'll pick the mask attribute. And from here, you can obviously cache this out and add materials and do your lighting and final render. So before we wrap this up, I thought I'd just go through the look dev and rendering I did for the intro animation, as well as some minor tweaks and changes I did. But the first thing being this null that I created. So I just created a parameter. I just found it a little bit easier to control the Vellum emission interval this way, instead of having to go into DOPS and change this value for the Vellum source and in the SOP solver for any wrangles that might be using the same interval. So that's the reason for why I did that. But I didn't want to include that in the tutorial as it's frowned upon in certain cases. But yeah, so that's why I have this null there. And I also played around a little bit with the sort of stiffness reduction that we're doing in the Vellum constraint properties node. So if you want the simulation to be more like floppy, I suppose, you can just lower this stiffness value. Otherwise, most of this should be the same. We're point deforming everything, and I'm just cleaning some attributes up. And in the intro animation, I actually cheated a bit, so I didn't cache out the extra simulation. I just cached out the essentially everything that happens after the point deform. Also, one little quick tip, if you ever come across someone else's files where they are referencing parameters left and right, you can actually see where this node is being referenced to in your scene graph by going to View and then click either Show for selected nodes or Show for all nodes. And this will create these lines just indicating that these nodes are referencing this node. So that's a little quick tip and good to know. So after I cached out the animation, I just added some normals, and then I added some colors to our geometry. I tried some different variations here using my Hex to ACCG HDA that I created. I'll leave a link to that in the description if you're interested, but this is a very quick and easy way to convert sRGB hex values into ACES. Worth to note is that this HDA has been updated since that video. So now you can also create Octane ramps if you use Octane. And it should be backwards compatible with older versions of OCIO as well. But yeah, I'll leave a link to that video. So I'm creating some colors, and the way I'm assigning the colors is just by creating a new random value based on that PID attribute, and then I'm just remapping it. I'm also creating a random attribute based on that same PID attribute, but with a different seed. And then I'm creating another attribute for shading purposes, and I'll show you how I use this attribute when we go into the shading in a moment. But all I'm doing here is just taking the luminance of those colors and comparing it to a threshold. So if the luminance of the color is greater than 0.7 in this case, it'll add this FAT invert attribute to the points. I'm then promoting the color and the random attributes. And on my primitives, I'm creating a group. So I'm just comparing the random attribute based on a threshold again. And if this condition is true, it'll just create this group for those primitives. So I'm then assigning a material, and then I'm assigning another material based on that group. So if I hit U and go up one level and hit render, we'll see that we get something in our IPR. And the lighting for this example is really simple. It's just 3 area lights and a dome light. I'll just zoom out here just so you can see where I placed them. So if we take a look at the shading, here we have 2 different materials. The first one is this sort of like memory foam kind of material. So in the memory foam material, I'm bringing this texture that I created in Copernicus, which is the new COPS or COPS 2.0 or 3.0. I don't know. So I'm just fetching a texture using a expression. So this grabs the full path to that texture. And I can just show you what that looks like. So I'm just bringing in 2 different bubble noise nodes, remapping them a little bit, and then blending them together just to add some detail. And this is what drives that memory foam sort of shader or look. So I'm bringing that in, I'm displacing it, but I don't think I actually use displacement in the end. But I am using it as a mask to blend between different versions of this color. So I'm using the RSPoint attribute node to bring in the color from the geometry. You can see here that this material only gets assigned on certain pieces, and that's being controlled by this group that we're setting here. So I get the color attribute, and then I'm just creating a couple of different versions of the color. One is just different gammas. And this then get mixed by the texture I created in Copernicus. Visually, it doesn't do a lot of difference, I think, but I was just playing around with shaders, trying to add some detail. And that's usually what I try to do. I just try to add a little bit of variance and detail, just to make it a little bit more interesting and dynamic. I'm also using that same texture to add some bump to the material. So for the second material, I've just gone ahead and zoomed in a bit on one of the pieces that have that material assigned to it, just so we can see it a little bit better. But yeah, it's pretty simple as well. I'm just bringing in that same color attribute. I'm then mixing the colors with this texture that I've created before. And the way it determines whether it should be white or black dots is from this invert attribute that we created in subs. So for the brighter colors, the dots will be black, and for the darker colors, they'll be white. So that's the reason why I created this attribute. So you can see here, I'm just adding a whitish color and then inverting it, and then mixing those based on that invert attribute. I'm then taking this color and piping it into the base color of the shader, and I'm also adding a color correction and piping it into the subsurface color, as well as the refraction color, but we're not actually using that, I think. That was just from when I was testing. So yeah, adding a bit of weight to that, mixing it with the base color, and then I just played around with the scale to get the look that I wanted, added some more samples. And then for the roughness channel, I'm using this texture that I'm probably going to be releasing as a part of a texture pack that I'm working on. So stay tuned for that. And then, yeah, same texture, adding a little bit of normal or bump, which is barely visible. But yeah, that's how I made this shader.
And that's it. If you watched this entire miniseries, kudos to you. I'm not gonna lie, this setup took me quite some time to figure out, so if you find any of the provided information useful, feel free to like and subscribe to this channel. The working file for this project will be on my Gumroad, and link to that will be in the description of this video. With that said, thank you so much for watching, and I'll see you in the next one.